Hi and welcome to this video about fork-join parallelism. In this video I want to demonstrate how to use multiple threads to speed up a computation and see what that entails. And also we'll try to figure out what's the best number of threads to use in order for the calculation to be happening in the maximum speed that we can master. So fork-join is just one type of parallelism. Sometimes it's referred to as structured parallelism. And here's the basic idea. We have a bunch of data you want to work with and you want to analyze that data in some way. So in order to make things faster, we're going to create multiple threads. Each thread is going to take a chunk of the data and work on that data. Once all threads complete the computation, we'll merge the entire results or harvest the results in some meaningful way. So in this particular example, I want to show you how to build a multi-threaded primes counter. That is, I have a range of numbers from to, and we want to count the number of prime numbers in this range. So we can definitely do that with a single thread, just go over a loop from to, and then for each number in this range, we can check whether it's prime or not. If it is prime, we're going to increment some counter and then we can get the result. So certainly this would work, but maybe we can speed things up by using multiple threads. Each thread will get its own chunk of numbers to work with, and it will count the number of prime numbers in this chunk. When all threads complete, we'll just add up the results coming from all these threads. And we'll try to figure out what is the best number of threads to use. So let's see how that could be accomplished. So I'm here in my Visual Studio application here that I created just as a simple console application in C++ called primes counter. And so the idea here is that I have some kind of function, let's say called calc primes, whose purpose is to get the from number, some to number, and the number of threads to use. I'm going to use just integers here. Of course, we could do something a bit more elaborate, maybe using potentially bigger numbers, but that's good enough for this demonstration. So what I want to do is to call this function with certain parameters. So I'm going to grab these parameters from the command line. So let's start with that. So we have argc and const character star for argv. And what I want to get here is just a number of threads from the application, from the command line. So let's say that we have here the number of threads to just be 1 as a basis. And if we have some parameter, we're going to take that value from the command line by using something simple like a to I. If you have at least one parameter we can work with. So we have that parameter, let's just grab it and turn it into the number of threads. So let's say that this is what we're going to do, very simple. Let's add some includes for this to properly compile. So let's start with stdio, and then of course we're going to use Windows APIs to create threads. We could use the C++ standard library, but at least in this example I'm going to show using Windows APIs to create threads. Maybe we'll do an example for C++ threads in a different video. So we have that, and now we can go ahead and call calc prime. So I have calc primes here. I'm going to give it the number that we get. Well, actually, we didn't specify exactly the range. I'm going to just select something so we can look at something just that makes perhaps being interesting enough. Let's say we have here 35 million, from 3 to 35 million. Of course, we can input that from the command line as well, but we'll just stick with this fixed range and number of threads based on what we get from the command line. And the number of primes we get here is going to be returned here as the return value for the function. Now, because we also want to know how much time it actually takes, we're going to grab the now here as, or let's call that simply start, and I'm going to use the simple function get tick count 64 that returns the number of milliseconds that elapsed since Windows started. It's not a very accurate function, but it is good enough for our purposes. And so now that we have that, we can look at the elapsed time as calling get tick count 64 again and subtracting what we had in start. Now we're ready to display the results. So we have primes, which is the value we got back from calc primes. We can say that elapsed was so and so milliseconds, and that's how the result is obtained. So elapsed is in millisecond, because that's how getTCount64 works. So that's all there is to do here in main, nothing very special else to do. Maybe just writing that we're going to use so-and-so thread. So let's write using so-and-so threads and add threads here. Okay, so now we're going to our next step, which is using this calc primes function. So what do we need to do here? We need to create a bunch of threads and let each thread work on its own chunk. So what is the size of each one of these chunks? So a size of chunk is going to be 2 minus from plus 1, because we need to include 2 and include from, and divided by the number of threads. Now, of course, this division might not be exact. There might be some remainder there, so we'll have to give it to some thread to handle, so we don't miss out on certain numbers. Now we can go ahead and start a loop. Number of threads we'd like to create. We're going to have a loop here running from 0 to threads, and we need to keep track of these threads using handles. So we need to have some kind of array of handles to work with. We can allocate this array dynamically using something like malloc, but I'm going to do something a bit more elegant and use make unique from the C++ standard library so that it cleans up the handle array automatically. And just need to add a little include here for memory to get support for make unique or the unique pointer. And then we're going to say that we need threads number of these items. So obviously I can use these handles at index I and use the create thread function to create a thread and track the handle in the array that we're given. So the first parameter here is security attributes, we don't really care about too much. So null is going to be fine. The default stack size 0 is fine, which selects a default stack size, which is good enough. It's about 1 megabyte as maximum for our purposes. That's perfectly reasonable. And then we have the start address. This is the actual function to be used to be called by each thread. It's going to be the same function, but it's going to get different values, different parameters. So let's call that calc primes thread. So that's going to be our function, which we have yet to write. And then we need to provide some data to the thread, and that data should include the from and to values to work with. So since we can only provide one pointer, we'll have to define a struct called thread data or something that has this from and to as part of its data. So we'll have to create a few instances of those based on number of threads and then fill each one appropriately before creating the actual thread. And of course, we also need to get the result somehow. We can add an item here for the result, or we can take advantage of the fact that the thread returns some kind of integer as part of its return value. We can grab that as another way of getting some result. But this is probably more convenient because the result is not always going to be an integer. In this case it is, but in more generic cases could be something more elaborate. So I'm going to keep count here as the output. So I need to fill in from and to, and count is going to be filled out by the thread. This means that we also need some array for the data here, for the prime data. So we're going to use the same idea here by using make unique and create a number of data structure of type thread data. This is an array and we need threads of those. So now before we call create thread, we have to prepare these data structures. So data I, that is going to be given to thread with index I. From is going to be, and we need to take here the from coming from the function and then take the index and multiply by chunks. That's going to be where we're starting. The first thread is going to start from, the second thread from plus chunk, the third from plus twice chunk, and so on. That's what we need to do here. I'm using parentheses here even though they're not strictly necessary. And then in terms of the to value, we hope, of course, we need each thread to take its own chunk and not step on the toes of other threads, so we don't want any duplication. But we also have to take care of that tail of numbers that might exist if the division to calculate chunk happens to be in precise and there's some remainder. So we'll do something like this. If the current thread we're looking at is the last one, so it's going to be I is going to be threads minus 1. Let's just give the last thread the to value. So the last thread is going to take care of any remainder that might be there because of the division that might not be exact. Otherwise, we're going to take what we have in data I.from and add to that chunk, but then -1, so we don't step over the data that belongs to the next thread. So we have that set up correctly for us, hopefully, and then we're going to pass this information, which is the address of data I, to that thread. For creation flags, there's nothing special to specify, and the last parameter is the thread ID that's going to be a result of that. We don't really care about that, we only care about the handle, although it might be perhaps a good thing to display something about that, but we'll do it in the thread call itself. Once we're done, we're creating these threads very quickly, so we create a number of threads here very quickly, and the threads are now running, doing some work. What we need to do here in the main thread is just wait until all the threads are done. So for this purpose, we're going to call the function wait for multiple objects, which in case of threads, we wait until the threads become signaled, which means for threads that they have terminated. So we need to wait here on the number of threads, which is threads, and then we need an array of handlers, which of course we have, and so we're going to use get to obtain the raw pointer to the array of handles. We're going to wait for all of them, so the next parameter has to be true, and then we want to wait for as long as it takes until they're done. And once they're done, we can return the result. In fact, we can harvest the results, which means basically going over all the threads again and grabbing the result. So we know that we have some count here we need to calculate. So let's zero out this count here. Let's add the data that has been returned here. That's going to be data I.count. We hope, of course, that the threads have filled out this particular member to indicate the actual number of prime numbers they have counted in their chunk. And as a matter of proper cleanup, we're going to close the handle for data for the handles that we're looking at right now. So we're going to close the handle so we don't leak the handles. Not too problematic in this particular simple application, but still a good habit to have. And we're done. We can just return count here. We're done. This loop is very quick. It's just adding some numbers, so it's going to be very fast. So we're not really worried about that. Most of the work is going to be done by the threads here, calling this calc primes thread function, which means that our next stop is this calc primes thread function. So how would that look? So first, it's a thread function, which means it always returns a 32-bit value. It's using the standard calling convention, which has meaning for 32-bit applications, and it has the name that we chose, and it always gets some parameter, which is in this case going to be our thread data. So every thread is going to run the same function, but going to get different data. It gets a different data structure, data I, that you provide here in the call to create a thread. So now we need to grab that data. So let's go ahead and do that. So we have the data. Let's just cast it back to a thread data. We know that this is supposed to be something like this. We're going to go ahead and now start counting the threads, the prime numbers in this range. So our loop here is from what we get here in the data as our from, and we have to go all the way to 2, so including 2, and for each number we need to ask whether it's prime. So I'm going to call a function called isPrime, which we have yet to implement. If I is prime, let's just increment our local count here. Once the loop is over, we're going to place the result in the count within the thread data structure here. So here's where the count is going to matter, and then we can return whatever because nobody really cares. I'm just going to return 0. So the last piece of the puzzle is this isPrime function. Okay, great, let's write this function. So isPrime is supposed to accept an integer and return whether this thing is prime or not. So how can we do that? There are several ways of doing that. I'm going to use one of these ways, and that would be to walk over the numbers from 2 to the square root of the number. So I'm going to go over the square root of n, and of course we have to do some casting here since it's not going to be necessarily an integer, but that's good enough. And if I go ahead and perform a loop from 2 to limit, including limit, and check whether the number is divisible exactly by I here, by one of the numbers from 2 to the square root. If this is the case, it is divisible without any remainder, this number is definitely not a prime. We can bail out early from the loop. If we're done iterating over the entire loop from 2 to the square limit and we didn't find anything that is divisible exactly, then this is a prime number and we can return true. And that's basically it. What we want to do, of course, is test how this actually works in practice. Before we do that, let's just have a simple printf here for every thread function saying worker thread and give it the thread ID. So just know that this thread has started its operation. I'm going to call the function getCurrentThreadID. Okay, so let's build that. Let's see if it all builds okay. It seemed to be fine. There's some bug here. So we have elapsed. Elapsed technically is 64-bit value, but we're going to do these things in a matter of seconds, so it's not really going to be that big of a number, and we're good to go. However, in order to test things related to performance, what we want to do is to compile in release build to make sure that we get the maximum optimizations from the compiler, all that stuff. So let's go ahead and use the command line to test these things. So I'm going to open a terminal or a command window here, doesn't really matter, in this directory. Well, actually it's going to be here at the bottom, which is good enough. So let's go ahead and go to x64 release and see what's going on. So the first thing I'm going to do is to run this application without any parameters. So we have primes counter, let's just run it. And that's going to use a single thread. So we need some kind of baseline to start with. So it's using one thread, and that's the ID that happens to be for that thread. So let's see how long that takes. And this should be something around maybe 16 seconds or so. So it might take a little while. So it takes 13.640 seconds roughly. So that's fine. We have a baseline to work with. So this is using just a single thread. Let's go ahead and use two threads, see what is going to change here. So this is kind of messy. Let me go ahead and open a normal command line window here to make it easier to work with. So let's go ahead and try this again. So we have primes counter. Let's do the experiment again with a single thread just to verify that we have something fairly consistent. By the way, at the meantime, we can look here and see that I have 16 processors, logical processors on my system. This is going to be important when we try to figure out what is the best number of threads to use. So again, it takes about 13.8 seconds. That's fine, pretty consistent. Let's go ahead and increase number of threads to 2. So now we have 2 threads working, as you can see here. They have different IDs. They're working at the same time. So what we need to verify is that the number of prime numbers that we get is in fact the same value, which will give us some confidence as to the algorithm, and then take a look at the time. So you can see here the prime numbers, the count of numbers is correct. That is, at least it's correct based on these two tests. So at least if it's wrong in exactly the same way. However, it took 8.9, almost 9 seconds. So notice that with 2 threads, it takes less time, which is good, which is expected, but it's not a linear improvement, which means that we didn't get half the time here. We get something more than that. It's not linear improvement. Let's now try with 4 threads. And I'm using these powers of 2 numbers just because it's easier to compare that to previous results. It doesn't really matter. I can use numbers that are not necessarily powers of 2. It's just a little example to use. So with 4 threads, we can see there are 4 threads working here. Again, we can see there's an improvement. The total is again the same, which means that probably we're working in the right way to calculate the prime numbers there. The number of the time it took is smaller, but again, it's not linearly consistent in the sense that if we have 4 threads, it's not the quarter of the time compared to the first run. We have here 13.8, and this is almost 5 seconds. It's about maybe third or a little less than that. Definitely not a linear improvement. Let's continue with using 8 threads now. With 8 threads, we expect things again to be better. Indeed, they are better. Now it takes about 3 seconds, but again, the change is not linear. compared to 13.8. We do get improvement, but definitely not 1/8 of the time. So now we're going to go with 16 threads, which should be the fastest that we can possibly get, perhaps, because I have 16 logical processors on my system. So if I have 16 threads, they're going to run at the same time, going to take all the available processors. So maybe that's the best I can do. So you can see here it takes about 2 seconds. Again, it's not a linear improvement. We started with 13 seconds and we get to 2 seconds, which is definitely better, but not a linear improvement, which we might have expected since we have cut the chunks in equal pieces, and that tail here doesn't really matter that much for this purpose. But what happens if we use more threads? Let's use 20 threads, see what we get. So with 20 threads, we actually get a better result. Even though it's not that much better, it's 2 seconds, here's 2.17 something seconds, still it is better, and perhaps it's kind of weird, why do we get here better results? We might have expected worse results. What happens if we increase the number of threads even more? Maybe it can get even better than that, and indeed it gets even better. So this poses some interesting questions. In fact, 2 questions are interesting here. First, why do we get better performance when we have more threads than processors? Because if I have 20 threads and I only have 16 processors, only 16 threads can run at the same time. There's just no way to run more than that. That's all the processing power that I have. And the second conundrum here is, why do we have improvement which is not linear? We add more threads. If we add twice number of threads, maybe we expect a linear improvement, so half the time. But this is not what is happening. So we have a very small improvement here. Maybe if we use more threads, we get even more improvement. Maybe, not sure. At this point, probably the improvement, even if it exists, it's a very small one. So we can continue adding number of threads. We can't use more than 64, by the way. And the reason is that the wait for multiple objects function is limited to 64 threads. So if I try to use more threads than that, the function will simply fail, and it's not going to wait at all for these threads. So you can definitely deal with that by doing something about that, but I think 64 is good enough, and you can see here that the numbers don't seem to improve anymore. So the question is why? Why do we have these 2 behaviors which perhaps seem kind of weird? And I recommend that you pause this video and think about it for a little while, looking at the code and see why this is happening. Why do we get improvement beyond the number of processors when you create threads more than processors? And second, why is the improvement not linear? In fact, I can give you a hint that both of these things are the result of a single reason. There's just one reason that causes both of these things to occur. So if you want to think about that a little bit, you can pause this video and then look at the code. In fact, the code I'm showing here is actually another hint that actually is here. The solution or the reason why we have this behavior is exactly on this screen somewhere. So we're back if you have paused this video, and if not, that's perfectly fine as well. The reason that we get this kind of behavior is that although we split the work here into equal chunks from the perspective of the range of numbers, it doesn't mean that the work the threads are doing is actually the same. In fact, it is definitely not the same. The first thread is going to work with very small numbers. And working with small numbers means that when you need to see whether a number is prime or not, it's going to be very quick, because we have a loop here that runs from 2 to the square root of the number. The smaller the number, the smaller the square root, which means that the quicker this loop will end. On the other hand, the threads that are later, such as the second thread, the third, and so on, they're working with bigger numbers, which means that the loop will take more time to complete for prime numbers, which means at the end of the day that all these threads are not doing the same kind of work in terms of load, which means that the first thread finishes first because it has the smallest numbers to work with, and then the second one will finish, and then the third one will finish, and so on. And when one thread finishes, the CPU is now idle, it's doing nothing, it's bored. And this is why when we had more threads than processors, it was actually helpful, at least for a while, at least until some limit. So for example, if I have say 17 threads, so the first 16 threads started running the first 16 chunks, say, and then when the first thread finished, because it has small numbers to work with, the 17th thread was scheduled by the operating system to working on its own part here. So the basic idea is try to keep the processors busy at all times. If you're able to do that, then you can get the most benefit from this kind of multi-threading when you have a CPU-bound operation, meaning operation that uses lots of CPU. There's no I/O here or anything. The processors are running all the time trying to do some work. And that's also why we don't get linear improvements, because when we add another thread, it is not linear addition. Still, the first thread will finish very quickly and the others will continue running, while the first and then the second and so on CPUs will become idle gradually. So not utilizing the full power of the processors. And that's why in general, to figure out what's the best number of threads to use for this kind of calculation, and of course this is a fairly simple example, is actually a very difficult problem indeed. And there's lots of research that has been done to make this easier. One of the things that we can do, which is provided by one of the headers that comes with the Microsoft C++ compiler, something called the parallel task, that allows us to actually do that fairly quickly without having to figure out exactly how to or how many threads to create. In fact, I'm not going to create the threads manually, but this is going to happen behind the scenes. So let's write another function here just for demonstration purposes. Let's call that calc primes parallel or something. So I'm going to grab the same kind of function name, but let's call that calc primes PPL. It's part of the parallel patterns library that Microsoft has. This is specific to the Microsoft compiler. It is not part of standard C++. And we can add and include here for PPL or something, PPL tasks maybe. Let's try that. And then we can use a function called parallel for. So parallel for, it's in its own namespace called concurrency, something like that. So we have parallel. If I added the correct header, if I didn't, then of course that's not going to work out. So let's start with PPL. Maybe PPL will be nicer to us, where this parallel for thing is defined. So if this is the case, you can see that it's here. There is parallel for here, and you can start from an index. And the basic idea here is to create kind of a for loop, but runs in parallel for every one of these indices. So you need to run from to 2, but we actually have to use 2 plus 1 here because it always runs exclusive of the final number there. Then we can provide some function to do the work. And we can use lambda function here because it's more convenient, where we get the actual number we need to work with. So in this case, what we need to do is to check whether the number is prime. And if this is the case, we need to increase some counter and then return that counter. So in order to do that, we might try to do something like this. And that could work, but in fact, it's not going to work correctly. And you might understand why this is the case if you watch one of my previous videos. But let's first try this. So calc primes PPL, what I'm going to do here in main, instead of calling calc primes, I'm going to call calc primes PPL, just to utilize the other function. In this case, there's no meaning to threads. Actually, I'm not going to use it really. Now, technically, we can just completely remove it, but I'm going to keep it here to make it easier to switch between the first function and the second function. As you can see here in this function, there is no threads here that is not really being used. And there's no kind of selection here, but the code is very simple, at least it looks very simple. Let's see what happens when we run this. I'm going to run this. The command line parameter doesn't matter anymore at this point. So it's not really using one thread, but you can see the count, the application finished in a fairly quick time, even quicker than what we managed to get before, without us having to actually say how many threads are being created here. However, you notice that the result is actually wrong. So the result is wrong, which means that it's not good enough. We first need to make the result correct and then try to make it as fast as we possibly can, not the other way around. We first need correctness. And so the problem here, again, if you've watched one of my previous videos, that we have a synchronization issue here. Because now we have this function being run concurrently by multiple threads. We don't know how many. We leave parallel 4 to deal with that kind of messiness. But we know this is going to run concurrently, which means that count plus plus is not a thread-safe operation. And that's why we don't get the correct result. So we have to fix that. And one way to do that is to use an atomic type here, atomic of int. We can initialize that to 0 and then use that for this purpose and return count. An atomic is supposed to be within the header atomic. Let's add that just to make sure. And let's see if it builds. Okay, seems fine. Let's try this again. So it's not really using one thread, doesn't matter. So you can see the result is actually the same in terms of time, because this plus plus thing as atomic plus plus is still very fast. And you can see that now the result at least is correct. So it's correct, which is the first thing we need to be aware of. And then it also runs very quickly. In fact, quicker than what we've done previously, which means that we've managed to do something which is very powerful here. Our code is very simple now. You can see the code is super simple. We don't create threads manually. We let Parallel 4 do the right thing. In fact, it does create threads behind the scenes, of course. And the way it works in a conceptual manner is that it always tries to make sure that all processors are always busy. So it gives a number to a processor, it calculates whether it's prime or not, returns a result, it gives another number to it, and so it manages all these tasks internally to keep always the processors always busy. When processors are busy, then we can get the best performance we can possibly can for this kind of algorithm where it is completely CPU bound. It requires to do some CPU work. There's no I/O here, just CPU work. And Parallel 4 is great for this kind of case. So there you have it. Here's how to create multiple threads. We can do that, but then we need to have much more complex code here to manage these threads, to decide how many threads to create, to segregate the data to the threads in a meaningful way or some good way, to try to balance the threads in some way, which we tried here in a very naive way, and we've seen that it didn't really work exactly as planned because each thread had different work to do. Parallel 4 here actually doing a lot of good stuff behind the scenes, simplifying our code significantly, although we do need to have some synchronization here. And so this count plus plus actually atomically increments this counter internally using a compiler intrinsic that's calling something like int or increment to tell the processor to do these things atomically. On the other hand, we didn't have to synchronize anything here with the worker thread because each count was local to the thread. So there was no need to synchronize anything, which makes the code simpler and slightly faster, but still overall, it benefited more with the parallelism offered by Parallel 4 instead of us creating threads manually. Still, creating threads manually is useful in some cases depending on your scenario. Thanks for watching.